Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell below. You'll get notifications for this series and a bunch of other ones on our channel. We're doing multivariable calculus. We're in chapter 3 doing vector calculus. This is 3.7, which is surface integrals. This lecture we're going to do orientated surfaces and surface integrals of vector fields. Last time what we did was surface integrals of functions of 3 variables. Now we're going to do surface integrals over vector fields. This is completely analogous to when we define line integrals for functions of 2 variables. Then we define line integrals for vector fields over orientated curves. Now we're going to do surface integrals for functions of 3 variables, and then we do surface integrals for vector fields over orientated surfaces. Let's do that. All right, for orientated surfaces, we're going to consider a surface S parameterized with the vector function r of uv at every point x, y, z on that surface. If there exists a unit normal vector which varies continuously over S, then we call this surface orientated. 2 of these surfaces are orientated, 1 of them is unorientated. Otherwise, we call the surface unorientated. As we try to do the unit normal vectors at every point on the Mobius strip, this is the Mobius strip, which has 1 twist in it. It's a piece of paper, you twist it once and then put it back together. Once I have that, the vectors are originally pointing inwards, and there's no way to have them continuously flip from being pointing inwards to pointing outwards, and this is, long story short, what we're going to call an unorientated surface. We're not going to give you unorientated surfaces because we can only integrate them over orientated, so we won't give you one that's not orientated. But we have to make sure that in space or physics or stuff that we're using, the description we're using, we can't start using these things to describe it. It has to be things that are orientated. Also in there, we say that if this unit vector now is going to have 3 coordinates, and x, and y, and z, if that z coordinate is positive, then we say that it's pointing upwards, the vectors, and gives us an upwards orientation for a surface, specifically when it's, this one is not, this is a surface which is closed surface in 3 space, which is not the graph of a function z equals f of x, y. This one is going to be the surface of a function of z equals f of x, y. In either case, if we can describe that the z coordinate is positive, that means that it's pointing upwards, and this is what we're going to call upwards orientation. For a closed surface, we're going to say that we have a positive orientation if those unit normal vectors point outwards from the surface, instead of, you could also have them all point inwards at every point, and that would be negative orientation. So positive orientation for a closed surface is essentially going to be unit normal vectors at every point which point outwards, and that gives us, the choice of n that we use gives us an orientation for our surface S. This is what we mean by an orientable surface S. Example 1, let's find the unit normal vector so you can see how to do this for the sphere of radius A. We've already done a parameterization of this, but let's do it again. How do we do this? And then specifically make sure that we have the unit normal vector so we can do this surface integral business over vector fields of orientated surfaces. First of all, the parameterization is r of phi theta is going to be, what is it? X is a sine phi cos theta. Y is a sine phi sine theta. And the z is a cos phi. This is spherical parameterization of a sphere. Surprise. Then what do I need? I need r phi and r theta. R phi is equal to a cos phi cos theta, comma a cos phi sine theta, comma negative a sine phi, and then r theta is equal to negative a sine phi sine theta, a sine phi cos theta, 0. Then we need r phi cross r theta, which is our parameterization. So their cross product is r phi cross r theta is equal to I j k. What do I have? I have a cos phi cos theta, a cos phi sine theta. Then I have a negative a sine phi. On the bottom I have negative a sine phi sine theta, a sine phi cos theta 0, which is equal to, once I calculate this again, I'm doing cofactor expansion along the top row, so block out this, and then I'm going to get 0, so I'm going to get a squared sine squared phi cos theta I plus a squared sine squared phi. When I block off j, I'm going to get 0, and then a squared and sine theta j plus a squared sine phi cos phi times k. That gives me my vector, and then what do I need? I need the normal of that vector now too, so let's move that up. Now we have r phi cross r theta. I need the norm of that to create the normal vector. That's going to be the norm of r phi cross r theta. It's going to be the square root of a squared a to the 4 sine to the 4 phi cos squared theta plus a to the 4 sine to the 4 phi sine squared theta plus a to the 4 sine squared phi cos squared phi. First of all, I have a to the 4 in each one, so let's take that out. That's going to give me a to the 4. Oh, and we have sine phi in some of them, so I am going to take it out. I have sine squared phi in all of them, so that leaves me with sine squared phi cos squared theta plus sine squared phi sine squared theta plus cos squared phi. Taking this out of the square root, I'm going to get that this is a squared sine phi, and then inside the square root I have sine squared phi, and then I'm going to factor that out, so I have cos squared theta plus sine squared theta plus cos squared phi. This is 1, so that gives me a squared sine phi times the square root of sine squared phi plus cos squared phi, which is, this is also 1, so that gives me a squared sine phi times the square root of 1, which is a squared sine phi. This is the norm. Now we're going to divide by that and simplify and see what we get. Now recapping, we have our original parameterization of the sphere, which was r phi theta is a sine phi cos theta, a sine phi sine theta, and a cos phi. We computed with great difficulty, probably you'll agree when you try these ones out. We created the cross product of r phi and r theta, and then we created their norm. What that now gives us is the unit normal vector, giving S a positive orientation is, I know it's positive because I've already calculated, and once you see it, this coordinate will be positive, but that's going to give us the positive orientation of n is going to be r phi cross r theta over the norm of r phi cross r theta, which is going to be now this guy divided by this, so it's going to give me sine phi cos theta, sine phi sine theta, and then cos phi. Notice that that means that n is equal to 1 over a r of phi theta, the original parameterization. This gives us our orientation of the surface S. We had surface S, which was a sphere. At any point now, it's going to give us the unit normal vector, which is, it's just a closed surface. And for an orientation on a closed surface, we say if all the n vectors point outwards, this is a positive orientation. If you want the negative orientation, negative n is just going to be r theta cross r phi. Because of cross product properties, it will be the ones that at that point it will point inwards instead of outwards. Now let's do surface integrals of vector fields over orientated surfaces. Okay, so definition, let S be a parameterized surface which is orientated, and we have specifically unit normal vector n. It's always going to be a unit normal vector. And let us consider now a vector field F, which is PQR over 3 space. In words, this is saying that the surface integral over a vector field F is the surface integral over its normal component over that surface S. This is also called the flux of F across S. All right, so how do we compute this flux, or how do we compute the surface integral over vector fields of orientated surfaces? We now have a definition which says that the surface integral over a vector field is actually equal to the surface integral over the normal component. So this is the vector field surface integral, and then this was the regular surface integral of a regular function. This is a scalar dot product. So what it's saying is how to compute the surface integral of the vector field is to do the surface integral of the normal component of that vector field, ds. If we have a parameterization of this surface S already, then we immediately have, well, you'll see, you'll have to calculate it, but then you'll have immediately an algebraic expression for the unit normal vector. What that does is I can put that into here and simplify. This gives us the integral of S of a vector field ds. First of all, how do you get rid of the bar? This surface integral over this vector field is the surface integral now over that orientated surface S, but now of the field's normal component, which is a scalar, f dot n ds. Now there's no vector ds. ds, remember, is going to have an expression as well we derived last time. This is equal to, now n, I know what n is. That is the integral over S, the surface integral over S of f dot ru cross rv over the norm of ru cross rv. And then ds is the norm of ru cross rv dA, which we derived last time for surface integrals of functions of three variables. Cleverly, of course, you can see this is going to cancel now. This says that the surface integral S over a vector field dot ds is equal to the surface integral over S of this vector field dot ru cross rv dA. Let's try that out at least once. All right, let's use the work of the previous example 1 to compute the flux of a vector field f, which is zyx, across the unit sphere x squared plus y squared plus z squared equals 1. That's going to give me specifically a is 1. So my parameterization is going to give me r of phi theta is going to be equal to what? It's going to be 1 sine phi cos theta sine phi sine theta cos phi. We saw last time that r, now because I'm going to use this calculation, we use the unit normal vector to calculate it and divide by that, but now because those norms cancel in the formula, all I need is r phi cross r theta. I don't need the norm. So r phi cross r theta is going to equal as a vector sine squared phi cos theta sine squared phi sine theta sine phi cos phi. We did this last time. A is 1, so it should be 1 squared, 1 squared, 1 squared. And then what do I want to do? Now I also need f of r of u, or phi theta. That's going to give us f, another vector, f of r of phi theta. Our parameterization is going to be now z, which is cos phi, comma, y, which is sine phi sine theta, comma, x, which is sine phi cos theta. Then what I need, again, I'm prepping everything before I put it in the pot and stir. Once I do that, now what do I need? I need f of r of phi theta dot product with r phi cross r theta, which is a horrible nightmare in notation, I understand, but this is now two vectors which don't look much better, and there's phi and theta. But this is going to give me cos phi sine theta sine phi cos theta dot product with this other horrible one, which is going to be sine squared phi cos theta plus sine squared phi sine theta sine phi cos phi. Dot product that, now I get a big giant sum which is going to be, what are we going to get in the first one? I've got sine squared phi cos theta, plus in the next one, that should be a comma, I get sine cubed phi sine squared theta, plus in the last coordinate will be sine squared phi cos theta. Now what are we going to do with that? We're going to take that hot mess and try to integrate it. What's our region now? Again, it's a sphere. So what are our bounds? We're going to be going from 0 is less than or equal to phi is less than or equal to pi. We're going from here to here is phi. And then we're going all the way around. So we're going to go from 0 is less than or equal to theta is less than or equal to 2 pi. With that, and this guy finally, which is f of r of phi theta, dot product with r phi cross r theta. Now we can compute that surface integral over this vector field. Let's try that. Moving that up and simplifying, this is now our dot product. This says that the surface integral over our orientated surface S of our vector field f dot ds is equal to the surface integral over our surface S of f of r of phi theta, dot product with r phi cross r theta, dA, where we now know dA is just going to be this bounds. That will now give me the integral from 0 to 2 pi, the integral from 0 to pi of this hot mess, which is 2 sine squared phi cos theta, luckily, plus sine cubed phi sine squared theta d phi d theta. Now we're going to have to compute this. Now you can see we need to know how to do cases of trigonometric identities, and now it will be extremely useful too. I'm going to split those up because I can separate everybody. This is equal to the integral from 0 to 2 pi of cos theta d theta times the integral from 0 to pi 2 times sine squared phi cos phi d phi, plus over here the integral from 0 to 2 pi of sine squared theta d theta times the integral from 0 to pi of sine cubed phi d phi. This one is 0 because the antiderivative of cos is sine, and sine at 0 is 0, and sine at 2 pi is 0. So that whole integral goes away if you're smart, or compute that, but you'll see that it'll take a long time. I'm going to notice what I cheated when I looked at a book where I stole this from, that yes, this integral, the integral of cos in a multiple of pi or interval of pi length is going to be 0. So all we have to do is compute this one then. Let's move that up and compute. All right, what we've done so far is we're trying to compute the surface integral over this vector field. We turn that into the computable definition of f of r of phi theta times our dot product with r phi cross r theta. Then we simplify that to this expression now. And what we're going to do is compute those two integrals. This is an integral of the trigonometric integral of type 4, where I only have even powers of sine and cosine. This is a case 1 where I have an odd power of sine and an even power of cos, because cos isn't appearing there. So how do I do those trigonometric integrals? This is equal to the integral from 0 to 2 pi. This one has to become 1/2 1 minus sine, or sorry, minus cos to theta d theta, and this one becomes the integral from 0 to pi of sine phi. I break the sine cubed into sine times sine squared. Sine squared is 1 minus cos, so this is 1 minus cos squared phi d phi. I'm now going to make a substitution of u is cos, and then I have the differential up to a negative. Using that substitution, I'm going to have this one is equal to what? 1/2 theta minus 1/2 sine to theta evaluated from 0 to 2 pi times this one is going to give me negative cos phi plus 1/3 cos cubed phi evaluated from 0 to pi. Once I do that, and I can put these bounds in, what do I get? Here again, this one is 0, and I'm going to get 1/2 times 2 pi times, and now here we have to be careful. This is cos of pi is -1, so negative is going to give me 1, and then here I'm going to get negative, so minus 1/3, and then minus cos of 0 is 1, so I get minus 1, and then I'm going to get 0 is plus 1/3, so that is going to give me pi, cancel, cancel, times, when I get this, I'm going to get 1 minus 1/3 plus 1 minus 1/3, which is equal to pi, 2 minus 2/3, which is 4 pi over 3. Our radius was 1, so the flux coming across this is directly proportional to the surface area. Surface area is 4/3 pi 1 cubed, and the flux was exactly equal to that. So please subscribe right here, hit the notification bell below, and I'll see you next time.